not much, but you could. Now it's going.
Okay, well, everybody is getting set up. I think there'll be a little bit of intro.
Yeah.
And then we'll get started.
Give us 5 minutes and we'll get started.
While we're waiting, I have a few books here. I have my card here. Anybody who's interested in working in quantum other than just information, take a look.
Settle out. Welcome everyone to IIT-AGNE's Tech Talk today on quantum computing. So I think as many of you know, Roopesh has been very, very closely involved with IIT-AGNE for many, many years. He's done a lot of work. He was the president before me. Roopesh was the president, so he taught me some of the ropes. But more recently, Roopesh has, his career has taken a slight turn, or for the better.
Huge turn.
And he has been, now it's been 2 years, working on quantum computing. And what we figured, Roopesh and I talked, there was at one point, there was a lot of news happening about quantum computing, where we are with the qubit stuff, who has supremacy, IBM or Google, who's doing better with all of that. But I think there's a whole different, another aspect of it around software algorithms and software environment. And that is what Roopesh's company is very closely working with. So we wanted to, and right now, you hear so much, all the news is dominated by generative AI. But this is a good way for us to actually learn some more about where things are with quantum computing. So I don't want to, without much further ado, I would like to hand it off to Roopesh. He can give his own introduction relative to quantum computing much better than I can. But before I hand it off to Roopesh, just one more thing I wanted to mention. IIT-AGNE, we always continue to do tech talks. The last one we did was, we had a workshop of using tools like Lovable. Actually, we had Lovable and people built websites. And before that, we had a talk on, so we've been doing a bunch of talks on generative AI and quantum and entrepreneurship. We have a few more lined up for the rest of the year. And if anyone has ideas for interesting topics, either that they want to talk about or that they want to hear about, please come find me, any of our board members, and we would love to continue to have this IIT-AGNE be the forum for all curious IITians to learn more of what's going on. And then one final thing, we are for the first time doing a family lunch get-together to welcome spring, summer. We have such a long winter, particularly this year. It's been exceedingly long and cold. But we have, on the 9th of May, we are doing a lunch at a restaurant in Foxborough called Sankalp. And we'll have karaoke, so bring friends, family along, and we'll enjoy that. So, it's again a good way. Our annual picnic is going to be in September as usual, the first Saturday after Labor Day, which is always popular. But for today, it is all Roopesh. And I am pretty sure we are going to learn a lot today from Roopesh. Thanks, Roopesh.
Thank you, Tui. Hey everyone, it's very odd to be on the speaker side of the equation. I'm usually the guy getting the samosas. I hope everybody's got samosas.
That's why we had to make sure that today of all days we had samosas.
That's right. So I bought about, I think, north of 2,000 samosas over the years for these kinds of events. So very interesting to be on this side. So I'll just describe to you what I'm going to talk about. So I knew zero about quantum in January of last year. I have to start by saying this. I knew almost nothing. I had read a couple of articles. I said, okay, what's this qubit stuff, right? And then I got recruited by this quantum startup that's out of New York and India called BQP to be their product team, head their product team. and which was my thing, right? So I've been a product manager for a very, very long time. And at Dassault Systems, which is just down the road, I led a product team for like many years, 5 years, 10 years. Not in quantum, it's in the area of computational fluid dynamics, thermal sciences. That's my actual thing. That's my actual background. And so I had to learn everything from scratch, basically. Everything from soup to from zero. And I read all these books, so some of those books are there. I have many more at home. And then I did my own coding, talk to the people who actually know quantum. So on my team, for instance, there's a 19-year-old who knows quantum better than me. So this is like a young person. I'll show you, I'll actually talk about why so many young people are there. So there's a boatload of young people who have gotten into quantum over the last few years, everywhere in the world, and they're all doing great things. And so the world is going to change because of quantum. It's eventually going to change. I'll show you the evidence today. And so I had to learn everything from scratch. What is quantum? How does it work? Actually write some code, actually run on a quantum computer, everything from zero basically. So I'm going to basically, you can think of it as I'm doing a brain dump of everything I've learned organized in some form. Okay, so that's really what it is. So I'm going to talk a little bit about the beginnings of quantum and then the history of this quantum computing area. And then I'll actually get into the fundamentals, the quantum fundamentals. So which is what I had to learn. I knew zero about it, so I had to learn. And so I'll give you guys a kind of like a very brief overview. There are entire books on this topic, so I'm not going to try to teach you everything, but I'll give you an overview of what it's all about. And then I'm going to talk about the future, right? Where is quantum going? Why is it going to take over the world? Why is it important for us to learn, especially the older guys like us, and for our kids? It's important for our kids to learn. Everybody hears about AI. At some point, quantum is going to be where AI is right now. Okay, so that is going to happen probably sometime in the next 10 years. So you guys are going to get an early preview of this. So I'll just start with the history. So who came up with the idea of quantum computing is this guy, Richard Feynman, and who's one of the very famous physicists of the 20th century. And Richard Feynman wrote this essay called Simulating Physics with Computers. And there's the first mention of a quantum computer. And his view was that, why are we doing computing our way? He was a guy who was always, questioning. If anybody knows about Richard Feynman, he was always questioning. He was always looking at the fundamentals. He's one of the great physicists of the 20th century because he was always thinking the other direction. So he said, why can't we do what nature does? Nature actually computes with quantum. If you look, I'll talk a little bit about that. So why can't we actually have a computer that runs on quantum principles, right? Because that's what nature runs on. And so, for example, if you look at your cup of coffee, it has caffeine in it. This is the caffeine molecule. And this is a very, very small molecule. It's got about 20 atoms in it, right? So if you look at from the chemistry point of view, right, from the number of possible configurations of this molecule is extremely large. So it's like on the order of about 10 power 73. And the number of bits, if you want to simulate this molecule and then come up with its behavior under different circumstances in great detail, the number of bits on a computer is 10 power 48. That's more than the number of stars. So you would need a massive computer, conventional computer, to actually figure out what caffeine is doing and the activity of caffeine. And in nature, there's even bigger molecules. So this is chlorophyll, right? So that's in the trees. This is DNA, right? And the chlorophyll and DNA molecules are way bigger, and nature actually computes and takes things. We may not recognize this computation, but in nature you actually are doing computation using. Our bodies are doing computation all the time with DNA, for example, right? So why can't we use quantum mechanical principles? That's the question he asked. And if you look at what are the principles, so this is an actual picture of DNA, right? So if you look at it, this is a SEM micrograph of DNA, and you can see that you can kind of see the structure. It's a little bit more fuzzier than we think, right? It's not as clean as the images we think. So in the quantum world, which is what actually where DNA lives, some principles it follows are everything is energy. Everything in nature is a wave as well as a particle. Many of us learned that in introductory physics. The act of observation changes a particle. So if you were to observe an electron, just the act of bombarding it with some light or something to measure that will change things. Okay. Superposition. Particle is actually not a particle. It's not a point. It's actually a smear in space. It's a probabilistic cloud. Basically, everything in nature at the level of atoms and molecules is a probabilistic cloud. And also quantum entanglement, which is one of those things called spooky action at a distance. Those kinds of things are really, it's out of the, it's not a normal experience. But basically it says that particles can remain connected across vast distances. A change in one instantly changes the other. That's one of the key cornerstones of quantum, as you know. Uncertainty, it says that you can't know everything about a system at any given time. You can know one thing or the other, but not everything. And everything in nature down there is probabilistic. So even this DNA molecule at the end is basically a probability cloud. Some cloud of probability. So that's the basic idea. And so then who came up with the idea of a quantum computer and what are the theoretical underpinnings? So these two guys, Professor Deutsch, who's at I think Cambridge, and Professor Josa, who's I think at Cambridge also, they came up with the fundamental ideas in the 1980s. So Professor Deutsch came up with, wrote this paper, which is right here for computer science guys. This is an important paper. It kind of laid out the overall architecture of a quantum computer, how it would work, what are the key elements of a quantum computer. So he kind of basically laid it all out. So this is kind of a foundational paper for quantum mechanics. And along with Josa, he came up with the first quantum algorithm. And I have this book here, which actually describes how that first quantum algorithm works. I was just blown away by the fact that this algorithm does in a single step what a conventional computer would take a very, very long time to do. It just does it in one step. When you go through the math, you're like, wow, in the end, it's like something very, very new. That you can have a quantum computer that solves a problem in one step that would take maybe days, weeks, years for a conventional computer to do. So that is one of the things that they came up with this. So this algorithm is called the Deutsch-Josa algorithm, and you can find code for it and you can run it. I've run code with small number of qubits, and you can see it in action. Right? So this is incredible. This really got a lot of people's attention. Then right here in Boston, there's Peter Shor, who's a professor at MIT, who came up with the Shor's algorithm, which is a very fast quantum algorithm to factorize any number into primes. Right? So you give it any number, it will factorize it into primes. And where is factorization of primes important? It's in encryption. So if you look at your 128, 256-bit encryption, it's basically factorization of primes. Very, very large primes, right? That's what they're doing under the hood. And so he came up with this algorithm, which is called Shor's algorithm, that can factorize any prime number. Now, this got everybody's attention because our whole civilization now lives off this kind of thing. The RSA is the foundation of every payment system, your passwords, everything is RSA. And so this got everybody's attention. And one of the concepts that came out is called Q-Day. I don't talk about it here. Q-Day is when all the encryptions in the world fail because somebody has got a quantum computer that's big enough to do this, right? And break every 128, 256-bit prime that's used there. And nobody knows. Q-Day might have already happened, but we don't know, really. So just to give an idea of the difficulty here, so somebody actually took Shor's algorithm and they used it to factorize a 39-bit prime. This is actually a small prime number compared to what's inside your encryption systems. And he used about 2,000 GPUs. So there's 2,000 GPUs there on a supercomputer to actually implement this and factorize this prime using Shor's algorithm. Now, this is actually a simulation of a quantum computer on a supercomputer that then did this job. And this is the farthest we've gone so far. So, but there will come a time when an actual quantum computer will crack all your password. It may already have done so somewhere in the world, which we don't know. Okay, the NSA or the Chinese, somebody might have already done it. We have no idea, right? So that was a big step, and that got everybody's attention. And yeah, we have even an IIT connection, which is that Love Kumar Grover was IIT Delhi 1981 graduate. He proposed Grover's algorithm, which is for database searches. So he was working at Bell Labs in the 1990s. So in 1996, he basically created this quantum algorithm. I'll talk a little bit about what this is in quantum algorithms and quantum circuits. But this is your algorithm. It's basically, it takes the information and then it passes through all of these gates and then finally it gives you an answer. So it's basically a search algorithm. It's a database search algorithm, and it's faster than the conventional algorithm. So it's let's not worry about the details there. but the more important thing is it's quadratic speedup. That is, if you have n things that you're searching for, or n records in your database, and you want that one record, you need order of n on conventional computers, and then it's order of square root of n on using Grover's algorithm. So this is a quadratic speedup. It's not as spectacular as the other two, but it's a practical algorithm. You could actually implement it, and people have also implemented this on an actual computer. And so it's also useful in encryption methods. So this is the next breakthrough that happened. Then then the speeds, then it became more of, okay, let's actually make a quantum computer. And so then what happened is that the first experimental quantum computer was made over in the UK. It was based on nuclear magnetic resonance, NMR technology. And then after that, there was a company called D-Wave, which is in, I think in Maryland, or no, it's not in Maryland, somewhere else. It actually released their first commercial quantum computer. So this is like the field started kind of developing, started getting attention. And then at that point, there's still academic tools, still research tools. This particular quantum computer, I think they sold a few. One is at I think Lockheed Martin, and people were doing things with it, but really not really taking off at this time. And then came the big event in quantum computing is the release of the IBM System 1, which is the first practical quantum computer which IBM really invested in. And it's the first integrated quantum computer. It's a commercial quantum computer. There's like several dozen of them and its successors in the world today. And this is what we think about when we think about quantum computing. This is what we visualize as a quantum computer. Now, the actual quantum part is all the way in the bottom, and the rest of it is just the supporting infrastructure. So it includes a dilution refrigerator, which I had never heard of before. It keeps the quantum chip down there at a temperature of just above 0 degrees Kelvin. It's like just above absolute zero. So this is the first practical quantum computer. And this quantum computer on the right is the IBM System 1. This is at RPI. So one of the interesting things that came out of my joining BQP was that they asked me to teach a course on quantum computing last semester at RPI. So I had students in my class. We used this to actually do projects with this, right, on this quantum computer. So it was very interesting. And in parallel, and this is also an important milestone, is that IBM released Qiskit. And Qiskit is a toolbox that can be used by anybody to write a quantum program. In fact, today I'll show you Qiskit and how to use it. It's freely available. Yeah?
So, taking questions now or later?
Later.
Yeah, I think let's relate.
I just was wondering how many qubits these were. But okay.
So the first one had 20 qubits. The more recent ones have about 120 qubits. And then they are now working on even bigger ones, actually. So if you look at the IBM roadmap, they've done a lot more there. Yeah, so this actually is one of the interesting, this is actually a major milestone in quantum computing. One of the reasons why this field has taken off is because they not only released a quantum computer, but they also released a software to go with it that anybody could use. Any of you can download and use Qiskit. You don't even have to download, it's available on Google Colab. I'll show you Google Colab. And then they also made it on the cloud. They have an IBM Quantum platform, which is on the cloud. And anybody who requests time on that, now they've shut it off actually because it's now become too expensive. But anybody who requests time on this could actually, they would give you a little bit of time. So you could, like the old time sharing computers which many of us had heard about, you could actually run on that. And you could write. And in fact, on my team at BQP, I have a 19-year-old, I have a 21-year-old. Around this time, they actually did this. They got time on this IBM System 1 in India, and they actually wrote a program and they ran on it. So that is one of the very interesting things that's happened. So anybody in the world who wanted time, they were just kind of giving it. If you showed them that you're serious about it, you've written your own quantum computing program using Qiskit, they will let you run. That's one of the very interesting things. And one other thing is, Qiskit contains a simulator of a quantum computer. That was the very first simulator that they of a quantum computer. So you don't need to actually run on a quantum computer. You can actually simulate its functioning using this thing, simulator, emulator, what do you call it? It's called AIR. I'll actually show you AIR actually today. Okay, so this was the big event. And then after that, quantum computing has basically exploded. Okay, so I'll show you the explosion also today. Alright, so I'm going to go to fundamentals, some mathematics required. Any questions before we move to the next session? Yeah, go ahead.
Can you get a copy of your slides?
Of course. Yeah.
We will send it to everybody who's registered on Eventbrite.
Thank you.
Thank you. Yeah, go ahead.
People still need to keep things secure, so once quantum computers break all our encryption methods, how are we going to keep our stuff safe?
That's
Your
a good,
son, your kids are your toughest audience.
Yeah, I'll answer that question. So one of the fields that is taking off is quantum cryptography, because as you'll see in a little bit, quantum has implications for even data and data's privacy and data secrecy. It has implications for a lot of things, so you'll see it in a little bit. Okay. Yeah.
So you mentioned about temperature, right? And how, I mean, that must be a really hard technological problem, right? To keep it at 0 point whatever, and
Yeah.
there's what decoherence happens.
I'll come to that. I'm going to talk about all this stuff. Okay, so you're going to get the complete view. All right, so let's talk about what quantum computers are about. So the first concept that you learn about when you talk about quantum computing is qubits. What the heck is a qubit? I had no idea actually, so I had to learn. So basically a qubit is taking advantage of superposition. That is, a particle can stay in multiple states at once. So if you look at your conventional binary arithmetic, which many of us are familiar with, on your computer you have bits, and then the bits can be either 1 or 0. So all your methods, everything that's on your hard drive is either a 0 or 1. It cannot be both, right? But with qubits, it can be both. And on a qubit, you visualize it as a sphere. This is called a block sphere. At the north pole of the sphere is 1, at the bottom is 0. And a qubit exists in all states simultaneously. It's a superposition. It takes all values between 0 and 1 simultaneously. So that's the superposition principle. And essentially what it means is that if you take one qubit and then you take another qubit, you basically have, I'll talk about that, you are representing information, all the information between 0 and 1 times all the information 0 and 1 on the second qubit, right? And then so you can do operations on this qubit. You don't know what the actual value is, right? So it's probabilistically between 0 and 1, some value. And then to actually get something definite out of it, you do an act which is called a measurement. I'll talk about measurements also. And so it's between 0 and 1, both 0 and 1, and then when you do the measurement, it picks one of them. So it collapses into either a 0 or 1. That's really what it is. So qubit is essentially information represented by all values between 0 and 1, and then when you measure it, it goes to either 0 or 1, right? So either one or the other. So that's really what it's doing. And one of the interesting things about qubits is that unlike a hard drive where all the bits have to be on your memory or on your CPU, they don't have to be next to each other. They can be entangled. That is, that they are interconnected, even if they are physically distant. And I'll show an example. So you can have a qubit here, one qubit in outer space. You change it on the ground, it changes up there, right? So yeah, so I think that's one of the interesting things, that if you take a problem and if you look at all its, let's say you have 4 pieces of information, and each one is 16 bits or 32 bits, which is typical, then to represent that information you need 4 times 16 or 32. But here you could basically represent it by just a handful of qubits. So that's one of the things that's a very interesting thing that comes out. And then what it also means is that if you're dealing with a problem, like a path planning problem, right? So many of us in computer science have solved like a traveling salesman or other problem. If you look at a path planning problem, if you're trying to solve this with a conventional computer, at any time with conventional bits, you would be basically representing one path, right? So you'd be saying, I'm going to go this way from my house to this way or this way, and then to my school. So if you look at your starting point and your destination, there are many different paths that are possible. But at one time in a conventional algorithm, you're representing just one path. But using qubits, you represent all the paths at once, right? So it's basically because of superposition, you represent all the paths all at once using qubits. So that's the difference there, that you are not making a definite choice here because it's probabilistic, it's superposed and entangled and all that. You are representing the whole problem in a handful of qubits, right? That's really what the advantage of this is. So if you're, for instance, this is a problem that has been solved, which is the shortest distance between all the state capitals in Germany. And this problem can be solved much faster than anything that's out there in conventional computer science. So the traveling salesman problem, path planning, that's where this stuff really shines. Okay, so that's one of the very interesting things about qubits. Then a little bit of math. How do you represent all of this, right? So the math is essentially that it comes from quantum mechanics. In quantum mechanics, and one of the properties of electrons is called spin. So either you have spin up or spin down. And typically there's a convention that spin down is 1, spin up is 0. And if you're looking at dots on a quantum chip, it's either 1 or a 0. So it's basically either 0 or 1. So that is essentially a qubit, basically. And so at the top is 0. So it means that you're represented by this vector. It's called the bra, and then the transpose of that is called a ket. And if you have a electron which is basically has an unknown spin, which is essentially your qubit, you basically have some value between 0 and 1. So that's the representation of that. So essentially it's linear superposition of all of 0 and 1. Every qubit is a linear superposition of 0 and 1. And then if you have 2 qubits, then the fun really starts, because then you get into what's called tensor operations. So you can have 1 and 0 together, and then this is the math. So it basically becomes a 4-dimensional vector, right? So this you represent 0 by a 2-dimensional vector, and which is called a ket. And then you take the other kets and then you multiply them together to get a 4-dimensional vector. If you're dealing with 3 qubits, then it's 8 dimensions, 2 power 3. If you're dealing with 4, it's 16, and so on. So what it means is that in terms of information, typically whatever number of variables you have in a conventional algorithm, you typically take a log of that. You take a log out of that, log to the power 2, and that gives you the number of qubits. And what it means is that any kind of information that is part of any algorithm, you need much fewer qubits to represent that information. That's really what it is all about. So because you are dealing with this kind of math, you're seeing that you're compressing information into very, very few qubits. And that is really the heart of the advantage that you get from quantum computing. Then once you have your qubits, how do you work on them, right? So in conventional computing, you have your gates, right? Many of us learned in computer science, first year computer science, and, or, not. Right? There's 3 gates, and then there's variations of this. There's NAND, NOR, XOR. There's a bunch of these gates that have been derived from that. In quantum computing, you have essentially infinite gates, and the actual number of gates which are generally used is about, there's 17 of them. I'm just listing a few here. These are the most commonly used gates. And what you're doing is that you're representing, you're essentially pushing your qubits through all sequence of these gates. That's what you're doing there. So I'll talk a little bit about these gates. So if you're dealing with a single qubit, operations on a single qubit, if it's a qubit is between 0 and 1, it's a point on the sphere, you basically can rotate that, right? So you can move it on the sphere by, you can rotate in the x direction, that's called a poly x gate. You can rotate in y direction, that's poly y, poly z, and you can, so you can rotate the qubit, move the qubit on the sphere. What you can also do is to put it in what's called an equally superposed state. So if your qubit is closer to 1 or closer to 0, it's at some point, you really don't know, maybe the probability of that is 0, because we are living in probabilistic world, or probability is low. What you can do is you can basically put it in a state which is called an equally superposed state. That's using a gate called the Hadamard gate. So these are all standard gates that are used. So this is a single qubit operations. And then you also have multiple qubit operations. So there's a C0 gate, and by the way, this is all matrix algebra for as you can see. So in the C0 gate, you have one qubit which is your control qubit, and the second one is a qubit you're manipulating. And if the first one changes, if the first one is 1, then the second one flips. So it's basically a bit flip operation. So you can actually do like a C0 of 1, 0, and because the first one is 1, the second one flips to 1. That's really what's doing. And the second qubit is 0, it becomes 1. But if it's 0, 1, so 0 is your your control qubit, and 1 is your qubit to be manipulated, then nothing changes. That's really what it is. So there are 2 qubit gates. There's even a 3 qubit gate. So this gate is called Toffoli gate. This one is called the Fredkin gate. Toffoli gate says that if the control qubits are both 1, then the third one flips. Friedkin gate says that if one of the control gates is 1, then the third one flips. Okay, so that's really, actually there's a swap, I'm sorry, it's a swap. So what it means is that if this is 1, then it basically swaps the second and third together, right? So that's what it is doing there. So you have 3 qubit gates, 2 qubit gates, 1 qubit gate. So it's a much richer tool set actually than what you see with standard computing. So the advantage of quantum comes in representing information by qubits. So you need much fewer qubits to represent information, and then you have much richer tool set to actually work on those qubits. So that's the advantage there. And then now that you have that together, just like with standard compute, you put a circuit together. And here essentially you start with some qubits, then you put them in equally superposed state using the Hadamard gate. That's something that you do. Then you do some operation to measure whether it's the right one or not. That's called the oracle. And then you amplify and do a bunch of things, and then at the end you measure the qubit. That's really what it is. So this is Grover's algorithm, which is the search algorithm. This is with 4 qubits. This is with many, many qubits. Right? So you can actually scale these. So one of the interesting things about this is that you can scale this. And so you encode your problem as qubits, then you push it through these gates, and then in the end you measure to get the result. That's really what the quantum algorithm is. So this is a new toolkit actually. It's a completely brand new toolkit, and it gives you a lot more potential in terms of what you can do with it in the future. So a lot of things become possible because of this toolkit. And then comes the measurement step. So this is basically what, at the end of every quantum circuit, you do a measurement. And then at that point, it collapses to a 1 value, as I mentioned. And so you're on the block sphere here, and then once you measure it, becomes either a 0 or a 1. Either it's at the top or the bottom. It takes a definite value. That's really what it is. And it's the last step in a quantum circuit. Okay, so that's the math for today. Anybody has any questions?
So they represent it also as complex numbers, right?
Yes. You can represent it as quantum complex numbers. Yes. Yeah, go ahead.
So so when it collapses, so it's any value between 0 and 1?
Yes.
But it collapses to 0 and 1?
Yes.
So is that a rounding function?
No.
How does...
Yeah, so it's a quantum property that if you have an electron, right,
Yeah.
so it is a probability cloud. It's here, it's there, wherever it is. But when you measure it, you get a signal value. It's either there or it's not there. Yeah, go ahead.
But all the subtlety is lost.
Exactly, yeah.
Yeah, as a follow-up to this question, how does that finally measurement give you a value of computation if it's always flipping to 1 or 0? If it is always between 0 and 1, a qubit is between 0 and 1, then the computation should give you any value between 0 and 1. So how does that make sense that it goes towards that?
I'll come to that. Yeah.
How do you do the measurement? What is the measurement?
It's a function. It's actually electronics for it that's called a readout. So you actually have either within the software there is a way that when you're done with all your operations on your gates, you actually hit it with a magnetic field or something, and then you basically measure it. Yeah. So to answer the question whether it's 0 and 1, one of the tricks that they use, and I don't understand it fully, to be frank, is that you can measure it at an angle. Basically, so if you look at it as a magnetic field, if you're hitting it with a magnetic field or electrical field, you can actually have it at some angle that that is different from the angle there. So one of the things that they look at is, the math is a little bit abstruse, I should say, is that you can actually get a value between 0 and 1 by the way you measure it. So that gives you can get a value between 0 and 1. So, yeah.
This is like the first thing, experiment of quantum mechanics, right? Where the wave particle
Yes.
thing happens, that you see the probabilistic distribution, but the moment you try to see it, it actually becomes
a definite value.
Definite value.
Right. That's right. Yeah. Right.
Oh, so just to understand, right? So the like you said, the algorithm, traveling salesman or whatever. So the fact that it can take infinite, probabilities between 0 and 1.
Yeah.
But can you explain exactly what is happening underneath? Like, as you said, the measurement could be 0 and 1, but if you think of a regular computing, in the way it is processing, how does the fact that it is, is it just that fact that it can have infinite values in between Is
Yeah.
that what is going to help the algorithm scale faster and that log 2, as you said?
Yes, yes. So there is a initialization step typically where you either you just do a random, it takes some random value and then you process it. And typically in there is this step, which is this block, which is called the oracle, which actually measures how far it is from the solution, from the final solution. So it's actually measuring. It's called the oracle block. I don't claim to understand everything there, by the way. There are people who know more than that. Yeah, right?
So, Roopesh, let's extend this traveling salesman problem.
Uh-huh.
So, if I had to write, let's say, Python code, I know what I am writing and what it is going, the conventional computer is going to do.
Yeah.
Does it change in the quantum world, the way I'm going to write the program? Or is the infrastructure going to take care of? I mean, I'm just going to write Python code and the quantum computer will convert it to, and then I'm like transparent to what is being done.
That is true. So essentially the quantum algorithm for solving this traveling salesman, it's typically an optimization algorithm of some kind. Actually at BQP we've invented our own algorithm. That algorithm will actually take care of everything. You just provided the parameters of the problem and it will solve it. So there's a higher level code, Python code. You can actually write it yourself. It's not that hard. I'll show you guys how to do it. Yeah, right?
So in the matrices you showed, I realized that the determinant of all those matrices is -1. Is there a significance to that?
Yes. So the matrices are what's called unitary matrices or Hamiltonian matrices. So the unitary matrices are, I think, if I go back here, they basically are, if you flip them, if you transpose them, you get the same matrix. That's what it means. That it's flip them or transpose them, they're called unitary matrices. So and the determinant is always 1 or -1. Yeah, right.
So the question I think was that Python code that you write. So it's just like a regular Python code now. So the transformation, that is where I think the intelligence must be, that
inside
transforms it
into
something which can be interpreted by.
Yeah, I'll show you. Actually, we have a demo at the here.
So does each computer have its own set of Python? Or?
Yes, IBM has Qiskit.
Meaning they have a limited set of Python APIs that you can use on that computer.
That's right.
Which is different from some other computer.
That's right. There are universal ones, but at this moment we are still early days. Still early days.
So okay, I get it.
Yeah, go ahead.
Some very basic technique. So if you have 2 qubits and each of them is in some superposition of between 0 and 1.
Yeah.
You just want to add them. How do you assign them a value? What does it mean to assign a value? What does it mean to add?
There's no assignment of value.
I want to do 0.5 plus 0.5. Like, what does it mean? Like, how do you think about this?
Okay. There are actually papers on this topic. I think the way to think about it is that you are starting with a probabilistic superposition of 2 qubits, 0.5, and then you're measuring somehow how far you are from 0.5 plus 0.5. And then your algorithm is actually moving towards that. And then when you measure it, you should get the numbers, which is 0.5 plus 0.5. That's the best way I can explain that. Okay. Yeah, go ahead.
So like in our conventional algorithm, can you log it and can you actually see what it is doing underneath?
No. That's the magic. You can measure it, but the measurement destroys it, right? Yeah. The measurement puts it at a different value. Yeah.
I think some of the algorithm questions just hold off because I think, Roopesh, you have...
I have a Google Colab folder.
And then you can talk.
I'll share it with you guys. Anybody, I put it on a QR code. You can all log in. You can see what it is all about.
But Roopesh, this means all NP-complete problems are now irrelevant, right? I mean,
no, that is my bread and butter now.
Okay.
So let's move ahead. I'll come to that. So one of the interesting things that comes out of this whole thing is what's called entanglement, right? As I said, if you change one, the other one also changes. So this is a little bit of math. So this is a circuit. This is called a Bell circuit. You start with 2 qubits. They can be 0 and 0. And then you put one through the Hadamard gate, and then you do another operation which is called the C0 operation. And at the end, what happens is that you get this. What this means is that either it's 0 0 or 1 1. It's not 0 1 or 1 0, right? So the 2 qubits are connected. What it means is that the qubits that come out of this after this operation, either they are both 0 or both 1, but they're not different, right? So that's what it means. That entanglement means that the two qubits are correlated. If you change one, the other one also changes. Okay, and this is one of the very strange experiments that have been done. They put two qubits on the ground into this state, that's entangled state, and they took one of them and they took it to space, outer space, and then they changed it on the ground, and then they measured it at the in space, and they found exactly entanglement. So it's action at a distance. You change one, and the other one also changes, right? So this has actually been done, and it has huge implications, right? And the number one implication is that you can't clone a qubit, right? So if you take a qubit and somebody in between actually intercepts it, and just to see what value, where it is, they measure it, and then that destroys the probabilistic part of it, and then you put it into another state, then there'll be a difference. Because what happens is that, so this is one of the very famous experiments, thought experiments. So we have Alice and Bob. Alice sends a qubit to Bob, and then he, along with that on an unsecured line, gives the Bob a checksum, right? Checksum is, the addition of the two numbers. So the qubit that he receives should actually have a certain checksum, right? That's really what it is. So if Alice, Eve in between, actually intercepts it and measures it and then sends the qubit, another qubit, then that will have a different checksum. That's really what it is. So it will have a different property, and so he will know. So you can't clone a qubit. That's one of the things that comes out.
Now, how do you get a checksum for a qubit?
No, it's so what you do is that you may have a way of putting it into your value, or you may what you can do is you can actually entangle it with a qubit on your end, right? So you can actually say, okay, if it has a certain frequency or some property, and then that property should match on the other side, right? It's a different type of checksum. Yeah.
So doesn't that the two qubits are entangled, that entanglement takes place instantaneously?
Yes.
If that happens, then how can Eve actually intervene in between? Because the two are already entangled.
Right.
How can she intervene?
No, what's happening is that Alice is sending only one qubit. So she has two qubits. She takes one she keeps, and then the other one she sends. Okay, so that's the thing. So the basic deal is that a qubit cannot be copied or cloned. That's one of those things. Huh? Yeah, go ahead.
Very quick question. What does it mean to send a qubit? Like, what is their entity? When you say, okay, they are like one is sent to space and one is on the, what does it mean?
So that's a good question. So it speaks to how qubits are made. So there's different ways that qubits are made. One of them is what's called a trapped ion. So you take an ion and you trap it inside an electromagnetic field, and then that represents your qubit. Or it's a set of ions. I'll come to that. And then you take that whole apparatus, including the whatever is there, and then you send it all to space.
But how is the communication happening?
That's the mystery.
That's a mystery. That's a mystery. Yeah, go ahead.
How does the state get preserved, of the qubit? If it's going all the way to space.
I'll come to that. That's a very important question, actually. That's one of the very important questions. That's it. Yeah, so this is one of the things that comes out, which is that it's no cloning, and then there's also what comes out of this is teleportation, right? So when I first read it, I was like, what the heck, this is like Star Trek stuff, right? And so quantum teleportation is essentially that you can send a qubit to space, and then you can change it here, change the qubit on the ground, and it will change over there. And so there's a cartoon here. When I send the slide, when you get the slide, you should take a look at it. The cartoon that explains how this whole thing works. So quantum teleportation is made possible. Yeah.
So information kind of is not restricted by speed of light by this. Right?
That is one of the mysteries, right? That's one of the mysteries of quantum.
This is what Einstein could not accept. Right?
Yes. There are people much smarter than any of us who've been, bamboozled by this. Okay, I'll come to the more practical part of it now. So those are the fundamental concepts. When you're dealing with quantum algorithms, what you do is you design your quantum algorithm, right? So there is a circuit, there's qubits, you put it to a quantum algorithm. So how do you run it on the hardware, right? So whether it's IBM hardware or D-Wave or whoever it is, how do you run it on the hardware? So these are the things that you do. This process is called transpilation. So first you feed your circuit to a software that does some amount of optimization. It takes a look at everything that you have, says, okay, is this the best way you can run this, and then it makes some changes. Then it breaks it into actual gates on the hardware. So on the hardware there's actual gates that you can run, and so on and on. And then it goes through and then places the physical qubits. It translates to the gates that are used on the actual computer hardware, and then it does a little bit more optimization, and then it runs that. Right? So there's a step. This whole step is called transpilation. Okay. So you define, just like with a conventional computer, right? You define your program. In the quantum case, it's a quantum circuit, and then there's a step. There's a bunch of steps before it gets to the actual physical hardware, right? And one of the interesting things that you find and challenges that you find is that very complex problem might require tens of thousands of these gates. So if you look at these gates, right, it might require tens of thousands. Kind of like a very basic overview of quantum. I have a demo. I'll do that at the end. I have a QR code. When you get the slides, you can actually run some of these programs. It's basically Python on Google Colab. So I've put a folder there that any of you could access, and you can actually just go in and you can copy the code and run it yourself. It's very easy to do. Okay, so I'll do that. Now I'm going to move to the next part, which is I call it the quantum computing explosion, and started with this, right? As I mentioned, so IBM System 1 really got this field going because IBM was very generous. They have, I think, somewhere around like 15 to 20 of these computers everywhere in the world, and they're available on the web. So you can go to IBM's website, and if they'll give you credits if you ask them, right? So any of you who wanted to see this quantum, you can ask IBM for credits, and they'll even sell it. Nowadays it's become commercial, so they're selling it to you. But in 2019, when very few people were doing anything with quantum, they were giving it away basically. And there are people all over the world who grab those credits. Like, that's where my company got started. And many of the kids on my team actually got credits, and they actually did stuff there. So for instance, we have access credits on a computer that's in Australia, and the guys in Bangalore actually, whenever they develop a new algorithm, they actually run it there, and they see how it works. So this Qiskit especially has enabled anyone to learn quantum computing. Huge numbers of large people, young people actually came into this area. Many startups got their beginnings running on this stuff. And this computer, for instance, was gifted by IBM to RPI. And so when I taught my course last semester, we solved problems and we did projects, and we had access to this thing, and we could run on this. And so we solved a bunch of problems on this computer. Okay, so this is one of those very interesting things that they have. So IBM actually, they started modern computing, and in quantum computing, they started this whole thing. All right, so as a result, what you have is lots of hardware companies that are out there. Quantum computing has really taken off. Lots of different types of hardware is being used to represent qubits. So there's superconducting circuits, there's photonics, which is basically photons. There's neutral atoms. I think there's a company down here out of MIT called QEra that's doing that. There's trapped ions. There's silicon, carbon, helium. So basically any kind of atom that you can control and you can change its state and do something with it, it can be used in quantum. There's developer and programming tools. So lots of different programming tools that you can use to make this happen. There's also hardware components and ability to control qubits and error correction, which I'll come to in a little bit. So there's a whole ecosystem of hardware as well as tools around quantum. So this is actually moving very fast. This is actually, every year there's a big jump that's happening. All of this stuff is evolving very quickly. And along with that comes the applications. So there's lots of applications. So we are up here, we are cross-industry, we are industry agnostic. There are companies doing drug discovery, financial services, chemicals and material simulation, optimization, logistics. These are all the areas. There's much more that's going on out there. So this field is evolving very rapidly. And it's still at an early stage actually. I'll show that to you. So there's middleware, there's applications and algorithms. And these are all the different technologies for the hardware. So superconducting, IBM Quantum 1 is superconducting circuits. There's trapped ion, which is this is out of University of Maryland. Quantinum was out of Honeywell. There's neutral atom, which is using rubidium atoms typically, so that's Q era. There's photonics, which is using photons. So there's psi-quantum, there's another Xanadu. There's silicon spin, so that's there's a lot of stuff going on there. There's topological, so Microsoft has gotten into that. That's their thing. There's diamond defects, so if you have a diamond crystal in there, defects in the crystal can become that. There's annealing, which is its own thing. So that's D-wave. So lots of different things are going on there. But
what does Google use?
Google should be here somewhere.
Quantum AI, you have something.
Oh, there, in the
On the top.
superconducting.
Yes.
Superconducting.
Superconducting, yes, that's right. So that's what they're doing. Now, where are we in terms of the size of these quantum computers? So, if you look at the number of qubits that are there, in the beginning, there are very few of them. So the first release of IBM Quantum 1 had 20 qubits. So you're all in the 10 to 20 range, and tens of qubits. But then as it's evolved, and right now we are getting into the hundreds, and some companies are getting into the thousands of qubits. Yeah, go ahead.
Are those actual qubits used for computing, or are they used for error code? You have to divide it by how many are being used for error correction.
That's a very good question. I'll come to that in the error correction. So the thing is that these are actually physical qubits right now, and then error correction also means more of that.
So it means more, or it takes the number down?
It takes less. Yeah, you have actual. So I'll come to physical versus logical qubits in a little bit. All right.
So these are physical.
Yeah, these are physical.
These are physical,
Yeah,
which is then partitioned into what you need for the computing versus error.
Error correction. Error correction. There's other stuff also that you
Okay.
need. Yeah.
So right now you're saying in 2026 we are Pascal is leading in terms
Yeah,
of the
that's a
number
French
of
company.
qubits? Okay.
That's at thousands. IBM is not far behind. QERA, which is in Boston, is also in the same.
So Google is pretty low down.
Yeah. Google
In terms of
actually is.
qubits?
Yeah. Sorry.
Okay.
But Google is honest, I should say, because they built an error connection in there. So they, I think they say it's built in. We are trying to make it so that it's error corrected.
Yeah.
Something called quantum supremacy, or something, which kind of compares what a traditional computer will never be able to do.
I'll come to that.
Okay.
I'll come to that. So this is
How do these compare in terms of energy costs?
a lot of energy. They're expensive.
I mean, how do they compare? Like some of them way over, and some of them are.
It's actually not the quantum, the little thing itself. It's all the supporting infrastructure to keep it cool to 0.1 degrees Kelvin. Keep it cool.
So who has better technologies to do all
At this stage, it's as clear as mud. I should say. I mean, some of them are doing well. Like IBM has been steadily doing very well. Others are coming up. QERA is coming up. Pascal is coming up. So, and I mean, it's still early days. I'll show it to you actually in a little bit. Yeah.
So some of this is roadmap, but also 2025. Did they actually make it?
Yeah, some of them have made. I think these roadmap and this is in circles is the
right. But also it's so IBM.
Yeah, some of them have made it. It's moving so fast that I don't know the actual numbers right now.
Is anyone making money?
Nobody's making money. Yeah. It's all hype at this moment. I mean, some of them are like D-Wave is actually selling computers. They're making some money.
But they're making profits.
No profit yet. Yeah, go ahead.
So regardless of the approach you take, does it still need the Kelvin zero?
Sorry?
Regardless of any of these approaches, like the diamond defect or whatever, you still need it at Kelvin zero?
Some of them, they have potential for being room temperature. They're promising it, but they're not actually delivering at this moment. Like Quantinuum here using trapped ions, and then like psi-quantum using photons. They say that it's room temperature, but they don't tell you about all the error correction that's going on still in the background. I'll come to why you need error correction actually. So I'll come to that in a little bit. All right. So moving on, quantum system applications. As I said, there's a lot that's going on, and these are all the applications that are there. It's going to really have an impact on everything that we do here. Eventually, there'll be a massive shift, paradigm shift, quantum shift, what do we call it, to using quantum computing everywhere. All the critical applications in the world that you can think of. So AI, batteries, electronic materials discovery, financials, everything is going to change. In every sphere of activity, eventually quantum computing is going to be there. So there's a lot that's going on. So what's happening right now is that because of the way you need fewer qubits to represent information, any kind of scheduling, transportation problems are in the focus, right? So because when you talk about scheduling of aircraft, there's like a billion possibilities, there's like literally billions of possibilities. So cargo loading ports, that's where the action is right now. Also because of the no cloning stuff, with a few qubits you can do encryption, de-encryption, communication, so it has impact on all of that. So those things are there. So for instance, this is what I mean, that if you're, this is aircraft scheduling or route scheduling problems, you can represent this with qubits, you can put it through a circuit, you can optimize and get the best answer. This is machine learning, so this is another area that we are working in. Machine learning also, we see a huge potential because machine learning and quantum actually go very well together, right? So if you're looking at AI, machine learning, quantum techniques are very useful because in machine learning, for example, when you build a network, right, of a deep learning network, you have typically 1 billion parameters, 2 billion parameters, those kinds of things, and you can represent them by quantum. So that's one of the things there. And machine learning, actually, one of the things we found because we work in this area is that if you put in qubits into your network, it makes it much better at learning and also to transfer to new data, what we call transfer learning. So many of you know that in AI machine learning, one of the things that's happening is that people are building foundational models, and then those foundational models are based on all the data that's out there. But then for your problem, you needed to learn your problem, right? So that is called transfer learning. That's the important step. So we find that if you put quantum in there, it's actually much better at transfer learning. So that's one of the interesting things there. All right, so I'm going to talk money now. So this area is exploded, as I said. So it's become a national security priority. Every country in the world needs to get into quantum. Everybody is getting into quantum. Governments are getting into quantum. And you can see that there's roughly $8 billion being invested, that has been invested. And these are all the governments that have invested. Every major government in the world is investing in this. India has gotten into it with 0.7, that's 700 million or 400 crores. That's called the National Quantum Mission. That's just gotten off the ground just last year. And we are talking to the NQM people because we are in Bangalore. Yeah.
How come China is missing?
No, China should be here. China, actually, nobody put it on the graph. China is also there.
They don't reveal it.
No, there are estimates there, but we haven't not done.
China has pretty high investment in quantum.
It does. That's a whole different topic. That's a whole different topic. Then, if you look at venture capital investor, private investment over the past 10 years, in the beginning it was very little, and now it's like grown like crazy. So in 2022, about $2 billion. I was looking at more recent venture capital investment. So last year was a big year. So there's $3.9 billion being invested into quantum with 111 deals being signed. Okay, so yeah.
Not to be the Debbie Downer, but this actually seems really small, right?
It is small compared to
like OpenAI raised 145 billion, all of this added together.
Right. But it's still compared to where we were, it's going.
But why do you think it's so small? Right?
Because it's still early stage.
This is 3.9 billion just going.
Yeah, that's right. It's just going. Now, if you look at the market sizes, there are people doing practical things with it. So the estimated market size in 2025 is about $2 billion, but there are all kinds of forecasts that are out there. So what this forecast says that in 2035, that is about 10 years from now, it's going to be $40 billion. This forecast says that it's going to be $21 billion in 2046. Nobody has any idea in reality. It's still very early days, but that's for sure that it's going to grow rapidly. That eventually when the breakthroughs happen, which I'll come to in a little bit, that it's going to grow by 10x, 100x. This is going to really take off at some point. Not yet, right? Okay, so I'm going to go talk about quantum error correction and logical qubits, which is where the action is, which is where the breakthroughs need to happen. So we talked about noise, right? So what's happening here is that ultimately a qubit is nothing but it's a photon or an ion or whatever it is, and you're basically hitting it with electromagnetic radiation, hitting it with lasers to make it do stuff, right? So what happens is that when you hit anything in like an atom or ion with any kind of pulse, guess what happens? It goes into a different energy state, and once it goes into a different energy state, it wants to degrade, right? And it immediately starts interacting with the environment. So it's decaying by itself. It's also getting hit by whatever is surrounding it, right? It's getting hit by light, by heat, whatever is out there. It's getting all that wants to come into and hit it, right? And what that means is that the lifetime of a physical qubit, once you take an atom or an ion or a photon and do something to it in terms of gates and so on, immediately it starts to decay and decoherence happens, which means that it's going to lose its accuracy. So you may have done this very nice expensive calculation, but within a few microseconds or nanoseconds, all that information will be lost. It's gone, right? So it's going to decohere and your results are bad. So this is what's called NISQ, Noisy Intermediate Scale Quantum. We are at this stage right now, it's called NISQ. And your machine can be, because there are small items, right, small ions, you may have hundreds or thousands or even tens of thousands of qubits, but it's useless because of the noise. And what that means is that you have to compensate for the noise. And the way you compensate is by actually using groups of qubits. You don't use one single atom to represent your qubit, you use a group of atoms. So you can have n of them, they are entangled together. Even if one of them is faulty, the others will retain the state, and then you can measure that, right? So that's really what you're doing there. So basically, to compensate for the noise and the error, you've got to really have multiple physical qubits into one grouping. Yeah, go ahead.
So if they are entangled and if one is corrupted, will it not take all of them down?
That's where the techniques come in. There are various techniques of compensating for that. Right? So that's what is happening.
Roopesh, another clarifying question. The entanglement is between all those computers in that one logical qubit, or is it entanglement is one-to-one?
No, it's all of them together.
All of them?
All of them together. You can entangle n of them together, right? So what I showed you is just 2 qubits, but you could have. So each one is a physical.
Yeah.
It's an actual atom or something.
Okay.
And then you have a grouping of them, and they actually represent your actual qubit. What's called a logical qubit.
So the qubit is not a one-to-one to an ion or an atom?
No, not at this stage.
Okay, thanks.
Not at this stage.
Yeah, that is
because of error correction. Yeah.
Got it.
The other thing that you use is these qubits, which are called ancilla qubits. These are essentially giving you an estimate of the error, right? So if something is going wrong, you have these, you're not doing anything with them. They're just along for the ride, and they are entangled with one or more qubits in your circuit, and then these are ancilla. They're not doing anything, they're useful. They're just a way for you to measure, okay, what's my error, right? And in the end, this becomes garbage you need to throw out. So if you look at most practical quantum circuits, they all have this ancilla bits at the end that they're there for the ride, basically. That's what it's doing there. Yeah, so that's where it is right now. There's a current state. And where we are going is, everybody's working on this. This is the hot problem. Can you reduce the number of qubits, physical qubits you need to represent a logical qubit? And can you correct for the error in real time? And then can you make a qubit that is long-lived? Because generally whatever you do basically in a short time, it will degenerate, right? It's going to degenerate. So you want to actually have a longer lifetime. And so this is the real problem. That's like at the heart of why quantum computing is not really growing as fast as it could. But people are working on these breakthroughs. So then when that breakthrough happens, then suddenly thousands and tens of thousands of qubits will become available, right? So then you can really go. And there's no memory storage right now with qubits also. So in a conventional computer, you have this magnetic technology that's used for storing, for memory and all that. That's it's not possible right now. But eventually it's going to happen. So we are here at the bottom rungs, and all of the stuff needs to happen to actually reach the potential, right? So then at that point you will have actual working quantum computers that will be able to do a lot more. And this is the vision actually. So we are right here, right, at thousands of qubits. If you make the breakthroughs and if we scale, there's several curves here. So eventually we'll get into millions of qubits. So those of us who've been seeing computers from the early days, right? We know that early computers had the first one I used had like 500 bytes, right? So the IBM Micro had, I think, 2 kilobytes, and then it went into hundreds of kilobytes, then it went into megabytes, and now we are into terabytes, right? So you can go down to Best Buy and buy a hard drive which has got several terabytes if you want to. So we are in that era, we are in the 1980s basically when it comes to computers, the quantum computers, and we have to go all the way up here, and then the real potential will get unlocked. So we are still at very early stage. And if you look at the forecasts, when we talk about quantum supremacy, we are here. That's all transient. It's very, very early. And then when it gets into more like thousands and millions of qubits, that's when things will become really interesting. That's when the real potential comes. And you're looking at it decades of time, basically, 20 years, 30 years kind of thing. Yeah, so this is where, I hope this answers some questions. Anybody has any questions?
So, even fundamentally, aren't we always going to be limited by the fact that you have to get this down to such low temperatures, because the physics is never going to change, right?
Well, you have to hold that thought, because if you look at conventional computers, where were we in the 1950s and 1960s, right? How were we storing?
But there were no laws of physics preventing them from...
Yeah, but if you look at those computers, early computers, they also had errors, like the bits would flip, right? So then there was a lot of breakthroughs that happened in technology to actually make it stable, right? So it was not reliable even in the early days. So we are actually all the way back there, right? Yeah, right?
I have a slightly different question. When you talk about quantum algorithms, and that's what we're looking at, and I'm still trying to wrap my head around the fact that this is probabilistic computation, and then you observe the results and you get the results.
Right.
Is this a repeatable process given the probabilistic nature?
No.
So if I give same input,
right,
run it once, I get an output.
Yeah.
If I get the same input, run it the second time, can I be guaranteed the same output?
It's probabilistic in the sense that if your answer is right, then you should get the right answer higher number of times. So as I said,
so in terms of even determining the answer is a probabilistic equation now.
Yes.
Oh my gosh.
Yeah. I mean, if you run some of it.
Yeah, go ahead. So you run the algorithm over and over again, right?
Yeah, that's what it's called shorts.
And then you choose the right.
That one slide of yours is very good.
Which one?
The one with shorts and...
The shorts, yes.
Yeah. So Roopesh, you mentioned one thing. You said storage doesn't work right now.
Yes.
So right now it's basically just computing.
Just pure computing.
Giving you an answer.
Yeah.
But so there's no. Do you have any comments on storage?
Not at this moment. I'll show you the quantum tech stack, and then maybe that will answer that. So this is where things will go. Yeah, go ahead, Surya.
One question. So I'm still trying to wrap my head around when you say that the computation is probabilistic.
Yeah.
What is error?
So error means that the state. I mean, it's hard to measure. You're right. The whatever state is in is some probabilistic number, and then. But the thing is that decoherence means that it is not that state. It is something else, and what the error is the difference between the expected state and what should be there. So if you hit an atom with or a photon with pulses of light, it will go into a different energy state. And because you know what the frequency is, you can expect that it's in a certain state, and then it comes down to something else. Okay, so that's the error. Yeah, right.
So here, is this the equivalence of like assembly language or micro language?
Yes. Yeah. That's what I was talking about transpilation. That's really what it is. So basically, this is how the future will look like. So you'll have a quantum processor here. These are the controls. This is a readout. That's the measurement step. There's an error correction step part here. And this is a logical quantum processor, which is essentially a sort of like a virtual entity. And then your algorithms live on the top. That's really the quantum stack there. So there's the actual hardware, and then there is a emulation of that hardware somewhere that is actually being used there. Yeah.
Is that the lower part, is that the logical layer is all software?
It's all software. Yeah. It's all
And physical is physical.
yeah, and this software can be on a GPU, right? This can be on a GPU.
Emulating the
It's
physical.
emulating and it's controlling.
It's like a microphone or
Yeah,
something.
yeah.
So that's really what it is. This is a general workflow. I mean, this is what we are working in. So there's all kinds of people doing this kind of thing, which is software engineering. There's a software engineering part where they're looking at QA, they're looking at development, that to run the machines, the whole stack there, right? So this is all that is. There are application developers, right? So that's BQP is one of them, and then the actual execution on a quantum computer. So that's the general workflow. There's lots of tools that are available. Any of you can use them. So this is one of the, there's a bunch of them. Yeah, right.
So the applications, are they still, they're pretty much just research, or are they actually being used in?
They're being used. We are doing stuff with them.
Okay.
Yeah, we're still.
But they're not commercially deployed. I think maybe the difference.
Okay.
That when I just want to make sure.
Yeah, no, that's what I meant. So are they being used, like,
Yes, they are. They are.
Real problems and
Real problems. Yeah.
Commercially deployed?
Commercially deployed. I'll come to the. There's some distinctions there. At the end, I have an advertisement for BQP. So there's an advertisement for BQP. We'll talk about that. Yeah. So I think coming back to this. So if any of you wants to learn about quantum, lots of tools available. Lots of different frameworks, tools. There's Q-tip. There's Qiskit. Circ is the Google one, Qiskit is IBM, there's Penny Lane, there's Project Q, Ocean, there's lots of them, lots of quantum development toolkits. Any of you can learn it. If you write software for a living, you can go and learn.
But you're learning one of these.
You can learn any number of them, nobody's stopping you.
But each one is different.
Each one is different, but the basic principles are the same, right? So the basic principle, it's just like the language, that semantics that's different.
It's like when you go to Python and you try to find something, there are 20 things you can find that do the same thing.
Yes, yes. It's the same thing. Yeah.
So this is like the SDKs.
SDKs, yes. It's kind of like the SDKs. No, there are toolkits. There's also SDKs.
Oh, so separate from that.
Separate from that.
Okay.
So there's two of them.
IDs.
Yeah. So Classic is the one that we use at BQP. So this is actually, you define your qubits, your algorithms, and it will actually then take care of the transpilation. It will say, oh, what's your target computer? It will do the transpilation. So this one is called, so Classic is actually very, very popular now. StrangeWorks is another one that's on the internet, so that's a web-based one. Yeah.
So you as a human are basically writing like something like Python code, and
it's
creating that for you. Got it?
Yeah.
I see. Got it.
Yeah. I'll show it to you. I'll show what Qiskit does actually at some point. And a lot of quantum computers are on the cloud. They're expensive, as I said, and there are very few of them. There's about 200 quantum computers in the world. So IBM has its own thing, IBM Quantum. Microsoft has Azure Quantum. Google has Quantum AI. There's lots of them. There's Azure Quantum. This is Amazon Bracket, which has got lots of different quantum computers. So lots of them are available. They're expensive. Right, like I said, I have somebody in my company who ran a calculation, which the cost of it was $400,000. Like, it was nuts.
What problem was he solving?
It was a very complex optimization problem.
Okay, optimization.
So, and he got funding from the US government to do it. Yeah, right.
Roopesh, how many actual physical superconducting chunks of computers are there in the world?
So IBM has around 20 of them, 20 to 30 of them. I think there's others like IonQ has, I think, on the order of tens. Does
Amazon have them, or?
They're all available on Amazon. You can go to Bracket actually.
No, but Amazon is just the top layer. Right?
It's just the top layer. But you have to buy the time. You have to pay them. Yeah, so it's expensive now. People have put small quantum computers with few qubits, 5 qubits, 10 qubits. Anybody can go and use. Any of you can go and use them. So, and in fact, you can buy one if you want to. So it's about $5,000 or so. You can buy a small one which has got 3 qubits for your home if you want one. Want to play around with it. So there's people who can do that.
Are they using this for like weather prediction and stuff?
Too far. Weather prediction is way
partial differential equation.
Yeah, we are doing work on that stuff. But it's actual application very far.
It's very simple. All the governments are using it to crack the darn codes.
Yeah.
That's all they do.
Yeah, exactly.
Hypothetically, the $5,000 computer that you can buy at home, does it also need a nearly 0 Kelvin cooling?
It has a small cooling circuit.
Why do you need a cooler?
For error correction, remember that in error, right, which this is what I was talking about, which is that as soon as you do an operation on a qubit, on that ion that represents your qubit, it's in a different energy state and then it degrades. And it also gets hit by heat, light, surrounding vibration, you shake it, it's going to change, right? It's very sensitive. It's very, very sensitive.
Roopesh, I have a question. So, considering the whole philosophy between probability and then the 0 to 1 infinite, if you give it a simple problem, so not like, where the traveling salesman, where you have exploring what are the different permutations, but if you give it an algorithm that, in our traditional computers gives you an output of, say, X.
Yeah.
Does this also give X, or does it kind of work counterintuitively here? Because, as you said, right, if there is error, you might deviate from that solution. So, is that a drawback? I mean, is it more for those things that your computer cannot do, or does it equally do well? The results are matching, right? Whether you do it the regular computers versus the...
That's a complex question actually, because you can do addition and subtraction. There are people who have looked at, what your calculator does, right? Your calculator does it very efficiently, right? So, so people have tried to do addition and subtraction, and if you look at those algorithms, they are extremely complex. They beg just to do something that you can do it, carry in your pocket. If you build a quantum circuit, the people have done that. There are publications on it, and you find that there is error. Because it's probabilistic in nature. So it's, if you do 5 plus 5, it gives you 10 with a higher probability than 7 or 8. It may give you a series of answers like 10, 11, 15, 8, but 10 will appear more. Okay, so that's really what it is. Yeah.
Can you qualify what kind of problems this can solve much better than?
Okay. So the kind of problems that it can solve are those which have essentially what's called combinatorial complexity, where the amount of information that you need to process to get the answer is so huge that conventional computers are struggling with that. So, like I said, scheduling problems, like if you have a port with thousands of aircraft landing, port with ships, or airport with thousands of aircraft landing, taking off at all times of day and night, it's very complex. And nowadays they use actual operations research type of techniques which are running on supercomputers, have huge compute capacity to solve them. But it's still very expensive to solve them. They're doing it because it's worth it. But with quantum computers, you might be able to take that and run it on a small quantum computer. Eventually, with 200 qubits, you could solve the whole problem. So that's where the potential is. So if you look at a typical aircraft, routing problem, right? So you have thousands of aircraft at any given time, and the system that routes it, there's huge compute capacity. We're talking about like terabytes of storage and lots of supercomputing level compute basically. So that's where you seek that. So problems which involve processing huge amounts of information are the ones.
So, I mean, kind of how many of these problems exist today?
Many of them, they're at the cutting edge of things. Look, drug discovery, for instance, DNA, like operations on DNA, any kind of DNA drug discovery, designing antibodies. I mean, there are important problems there. Folding.
So I think
protein folding.
Related to that, a lot of it is like anything that's tree traversal, like at an abstraction level, right? Anything that's related to tree traversal and that, a node, end nodes and edges, and that a classic whatever we learned way back.
That's right.
That's the classic problem. But I have a question to that. So, how do you, does each problem you pick up, do you program it differently today in quantum computing? Like what you folks are doing? Like this, each one has its own unique algorithm?
That's a good question. We work on general purpose algorithms. There are people who do specific algorithms, like drug discovery. We are looking at protein folding, design of proteins with huge number of variables, huge number of possibilities. So those people are doing specific things there. What we are working on is general purpose algorithms. So people are doing both.
So those general purpose algorithms, are they the conventional algorithms done on quantum computers, or are they entirely different?
Entirely different piece. Using the toolkit. So I talked about gates and so on, right? So you actually use that.
So the algorithm itself will be different. You have to figure out the algorithm now in a quantum.
Yes. 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 Yeah. Right.
So I guess in the quantum computing, every answer has an error and a probability.
Yes.
And your right answer is what you get the most.
Yes, highest
But
probability.
it could also still be the wrong answer. So how do you know what's the right answer?
That's the key question that you're asking. We actually don't know. So there is a lot of calibration, lot of benchmarking you do. You run problems that you know the answer to in the beginning. Yeah, you're right. Yeah, go ahead.
So you talked about storage. It is not handled yet.
No.
So when they're modeling these problems, then are they all stateless problems right now? Like you're writing the algorithm without any state?
Yes. So the state is changing. You start with the initial state that you can initialize, or you do it at random, and then you put it through this quantum circuit, and at the end, hopefully, probabilistically, you have the answer.
Right,
so you have the final state.
Yeah, but my question is this equivalent to functional programming where we don't have state, like a stateless program?
I don't know enough to answer actually.
No, so if you take the gravitational problem, right? Where do you persist that information that there are 4 nodes and there are these paths?
Okay.
Where do you
That's
persist
the initial setup.
That's
right?
the way you map it to qubits. It's part of the mapping to
setup.
qubits. So your algorithm actually maps the qubit.
So you need enough qubits to have all
Yes,
of this?
yes, that's the key thing there. So one of the problems is that one of the issues that we face is that we run it on small problems which we know the answer to, but eventually you get to problems which we have no idea what the right answer is. Okay, so it's very hard. At that point, it's anybody's guess. Okay, so still early days.
You have.
So I noticed that on the software slides, like there's like circuit, and like on those you like are making your like a separate quantum circuit for each algorithm.
Yes.
Each program.
Yes.
So then, how does that like translate onto like a physical computer?
Yeah, so there's a step called the transpilation step, and in transpilation, there is software that does that. That takes whatever circuit you design and the qubits, and it translates that into actual physical qubits and physical gates on the actual computer, on the actual hardware.
So the physical hardware can be modified, like on the go.
Yes, yes. On the go, it's being modified. So it's basically a bunch of atoms or ions or photons that is getting hit by an electromagnetic field. That's really typically what's happening. It's change its state. Okay. Yeah.
So just to make that a little clearer for me, you're talking about using general purpose computers to kind of create the program that finally runs on the quantum computer.
Yes.
So it's like a batch job thing, so to
Yes.
speak.
Yes.
Different question. Going back to error correction. So today we use FEC. Without FEC, a lot of computers would work, and a lot of transmissions would work. Where are we in that state? I mean, is there a way to,
Still early. That's why I was telling you guys, right? Which is
it's even before FEC.
Yeah. We are here. So look at where we are. We're here in 2025. We need to be here. Okay, and that's 20 years.
That's a lot.
20 years.
No,
of
no.
work. Yeah,
Could be anything.
decades of work.
Could be anything.
Yeah. The breakthroughs have yet to happen. Yeah, so it's still early days. So I want to talk about BQP. This is the advertisement. This is what I've been paid for, right? So BQP was started by 4 young guys. They were stuck at home during the pandemic. One of them was a grad student at RPI. The other one was a grad student at Minnesota. And they were talking to their friends about what they're doing. They're actually fluid dynamics guys. That's one of the reasons they hired me. That I'm a fluid dynamics guy also. And they realized that what's happening is that compute power has increased, but the algorithms have not. So that's one of the things they've seen. Compute power has gone up by like huge magnitude, right? Where we are now, huge magnitude in terms of what's available. But the algorithms are still the same ones that were invented 30, 40 years back, long back. So they said we got to work on simulation algorithms. So that's our background. And so this is what. This is what we are all about. So we take, here's the classical algorithms which use a fraction of the compute power. This is where we are. we want to invent first algorithms that are quantum inspired. Using the toolkit of quantum, which is qubits and gates and circuits and all that stuff, we want to invent new algorithms that we can run on current GPUs. We want to get more throughput, more out of the current hardware. And then the same algorithms at some point, or a form of them, will run on actual quantum hardware. So we want to be ready when it really starts taking off, right? So that's the basic value proposition of this company. So it's 95. So basically, this is where my job is. But eventually, my job will evolve to that. Like if I last that long, right? That's all. So my job will evolve to that. So that's when the real value will come, when you'll be able to get more out of these things.
You can clone yourself to a future.
Yes, but there's no cloning.
So, also 10x throughput, sorry.
Yeah. So what we think is that using this new toolkit, we can get more by, because you can represent information as qubits, you emulate qubits, you emulate gates, and in your algorithm, you should be able to get more out of it, out of current hardware. And then when we actually get to actual quantum computing, we should get more, even more, like 100 times more. That's the vision, right? And we are working in 3 areas. So one is optimization, as I mentioned. So that's the hot topic now, because you can do something right now. We're working on physics problems, so simulation, CFD, fluid dynamics, all of that, weather simulation. It's still early stage, though we are seeing some good things actually. We are seeing some good things there happening, but still early stage. AI/ML is another area we're working in, because one of the things we find is that AI/ML, there's huge potential for improvement, or even on the convention, even though it's supposed to be mature, there's still huge potential for improvement. And so we have right now what we call quantum now. So that's the solver. That's what I'm responsible for, to commercialize, build a product, commercialize. That's my thing. And then there's quantum max, which is on the native side, and quantum native, which is running on actual hardware. So we're working on all of this. This is further out. This is what we are doing right now. And the idea is that we should get benefit of quantum now with today's hardware, and we should be able to move fast, solve large-scale problems, and all of that. And one of the things that we are doing is we are building integrations. So we want to essentially make it such that we have a Python library, we have a MATLAB toolbox. You can just plug it into existing systems and use them. So plug and play is what we are trying to do here. So that's the advertisement. I do have a demo, but I'll take questions first.
That's all. Can you talk about like AI/ML a little bit? Because why and how quantum computer is more suitable for AI? I mean, if we talk about the neural network and talk about forward pass, backward pass, how is this more suitable?
Okay, that's a good question. We actually have a paper on this, scientific paper on this. So the basic thing is that if you look at a neural network, right, it's got weights and biases. So we have a deep network has 10 layers, and each layer has thousands, some number of neurons. They're all interconnected. Right. So the total number of weights and biases or connections is on the order of tens of thousands. If you look at LLMs, they have billions of those, huge number of connections. But their problem is that they are actually specific to the data that they are trained on, right? So if you look at LLMs, right, whether it's ChatGPT or whatever, they are actually using actual physical humans to verify the data, right? At the end, they're doing actual verification. So what we find is that outside of the data on which it's trained, it has to learn. First of all, it takes a huge amount of compute power. As many of you know, training of LLMs is extremely expensive, right? Because of the total number of parameters. Whereas with qubits, typically the number of parameters is small. The gates that you use are small number of gates, they are parameterized, but the number of parameters becomes very, very small, much smaller. So you can reduce the amount of training that you need to do. So that's the first part. Then the second part is, because this is probabilistic world, to train with new data is much cheaper. They're much better able to train on new data. So transfer the learning. So nowadays, what they're doing is that in every field they're building foundational models, which are based on all the data that's available, and then they are doing transfer learning to the new data. And what we find is that it's able to do a much better job of transfer learning. with lesser effort. That's really what it is. Yeah.
So I'm really confused about the state of quantum computing right now because problem solvers for MATLAB make stacks quantum ready days. But if we are decades out from real usage, like who is doing it in, like who needs it in days right now?
So there's still problems. There are problems that are being solved, like GPUs. You can run it on GPUs, right?
But I think the answer to your question is that intermediate. You know, you have these three circles. Is that intermediate one? Is that using quantum? Yeah, this is where today.
So it's you're kind of simulating quantum through GPUs.
Yes.
Quantum-inspired algorithms.
Yes.
Quantum-inspired algorithms running on today's CPU and GPU. So like MathWorks has, you know, we have, they have a toolkit. MathWorks has some libraries for quantum, which is, I think it implements Grovers and Shores as far as I know. I don't know the details of it, although I work there. But I think it is to allow then model simulation on top of it, which is the actual application, engineering application layers, to use some of these algorithms to build on top of that and do the same computation more efficiently. Because some of these simulations are just such a long, you know, they go on for days and months, and now you can start to collapse.
That's right, that's right. So, yeah, go ahead.
There was a question on NP complete and NP hard problems. So
what we call quantum now, we are focusing on NP hard problems right now. So these are scheduling problems. For instance, we are working on space applications. So in space, there's scheduling of satellites. We are looking at propagation, calculating the probability of collisions between satellites. Nowadays, that's become an important problem. Those kinds of things. So there's lots of applications.
Given you're all fluid mech guys, you didn't want to solve turbulent flow.
You want to, but it's too hard.
Yes, I guess it's like weather prediction.
Yes. Okay. Anybody has any other questions?
Yes.
Yeah, go ahead.
About your company, like how is this sold?
So what we are doing is that it's a Python library that you can actually buy and plug into your system, or a MATLAB toolbox you can buy. At this moment, we are still at so early a stage that I'm like, okay, people just use it, right? We want it to be used.
So, Roopesh, you don't rely on the actual hardware. You're providing the emulators, so to speak.
Yeah. So to speak, yes. Yeah, right.
So, with the tiniest quantum computer, let's say 3-4-bit computer, what kind of problem could you solve?
You can implement your own version of Grover's algorithm just to play with it. At this moment, it's too small. You can just play with it.
So like Fourier transforms is one of the things that
you can do. You can do stuff with it.
Fast Fourier transforms.
Yeah, go ahead.
So how many qubits can you actually process on GPUs in some reasonable number of times?
Oh, okay. So because we are emulating, we are not limited by all the error correction and all of that. That doesn't exist.
You're limited by time, right?
You're limited by time.
How hard a problem can I give it?
Yeah. So just to give you an idea, so the fastest calculation, biggest calculation we've done is for training an AI/ML network for some kind of an engineering problem, which has got 2 billion parameters. So 2 million. 2 million. We are talking to people who are doing 7 million. And on a GPU, right? If you know what the structure of a GPU is, it's got like all these small cores, right? These tiny cores. So like the top end, like the H100 NVIDIA has got 18,000 cores, small compute cores. Those are going to be basically those can handle that kind of problem. You just need, and we can do it all in parallel basically.
So maybe I ask the question in a different way. If you ran that with standard algorithms, it takes X amount of time.
Yeah.
If you ran it with quantum now, what would it take?
It's about 20 times faster.
Okay.
10, 15 to 20 times.
So what's the largest, have you run Shore's algorithm on it? What's the largest number you factored? You had this 39.
No, we don't do Shore. That's that's its own quantum circuit. What we are doing is we're developing a solver for optimization. At this point, it's a general purpose solver for optimization. That's it. We are not doing any of that. That's yeah.
Can you go into why there's so many young people?
Because young people like to play with new things. Right? Either you be young or young at heart, right?
Right here.
I mean, I should say that when sometimes I'm in the room in Bangalore and there's like, everybody is at least 20 years younger to me. I'm like, okay, what am I doing here?
I had a boss who used to say they're uninhibited by constraints that the rest of us. We keep thinking about why you can't do it. These guys, they don't know.
Yes. I mean, young and foolish always works, right?
It works.
Okay, all right. I think
check if there's more you want, otherwise we open it out.
Yeah. I think we've had
It should be good if you can show a little demo.
Yeah.
I don't know, people, what do you all think? More questions? I think it'll get us a better feel.
Yeah, I'll because I created a few demos today, and these are, any of you guys can run this, by the way. So I'll open one of them.
Wait, do you have that particularly powerful computer to run these demos?
No, these are very basic.
By the way, you never answered his question.
I'll answer it home.
And then you will tell us, right?
I already know the answer.
Okay.
I already heard the answer.
Yeah, so let me just go to my Google Drive.
With quantum computing.
And I have a bunch of these gates, right? So I have created my single info. Okay. Okay. So this is the.
So you write it in a Jupyter notebook.
Yeah.
Jupyter notebooks.
Anybody here can use it. I'm just putting it out there for anybody to use. So this is Qiskit, and you load whatever you want. You define a quantum state. You excite it. You put it into superposition. General qubit state, visualize states on a block sphere, plot it. You can do all this stuff.
Can Claude Code write this code out? Can Claude Code?
It can.
Have you tried it?
I haven't actually tried it yet. No.
Okay, I'm going to run this.
Your homework for today.
Okay, so let's see. Let's run this. So it's going to run, and it's, you're installing Qiskit right here, and
it uses Rust also.
So this is an emulator, right? It's running in an emulator, right?
yeah, it's Qiskit. It's using Qiskit as its emulator. Of course, it's not a real quantum computer. I would be paying a lot of money for this. This is free.
Yeah.
This is free. So this is a qubit in the initial state. Initial state is 0. You excite it, it becomes 1, and then this is a superposed state, right? So it's somewhere between 0 and 1. That's really what it is, the general qubit state. So you guys can run this. I'll open another one. And I'll do a demo of a gate, like this one, maybe this one, Friedkin gate, right? So this is a 3 qubits, install, so air is their simulator, it's their emulator, and then you basically...
Can you go back to the in setup phase? I think that's an interesting part, like how do you initialize these things?
Okay, so you first create your quantum circuit.
You give it how many qubits?
How many qubits, and you also can give 3 classical bits. You can set up the quantum circuit, and then you initialize a couple of the qubits, and then you can visualize it, and then you apply the quantum, the gate, whatever it is, this is CS swap, and then you can plot it, and then after that you can measure, and you can also do a simulate, which is the probabilistic part. I want to show this, right, because then I run all of this. So this is the initial state. So qubit 0 is at 1, qubit 1 is at 0, and then qubit 2 is at also 1. I think that's what it's right. After the state, because remember, if this is 0, if the control qubit is 1, then these two swap. These two swap. So you can see this one, the top one becomes 0 goes 1, and then 1 becomes 0. So that's swap. That's a gate. And okay, it's still running. So that was the result from today morning when I ran it. You'll see it. Yeah. Okay. So this is it. And then this is the measurement results. So it's 0, 1, 1. So when you measure it, it should give you 0 for the first qubit and 1, 1 for the.
But it's
It's not.
It's not yet. It's not
yeah.
there. It's not. It's going to come, I think.
It's
So-
still computing.
It's still computing, I think. No, well, maybe 011, Q1 and Q2. Okay. Yeah, sorry, I got that wrong. So this is qubit 0 is 1. And then,
But you started with 1 and 0.
yeah, no, I think it's the order that's different. So you should, yeah.
The control seems to be.
Control seems to be,
How do you measure a
Read it
qubit?
right to left, it's okay.
yeah.
Unless it's Little Indian.
How do you measure a qubit?
That is its own thing. Okay, I'm going to do a no cloning. Okay, this is no cloning. So this is the Alice Bobbin. So this is the same thing. So I'm going to run this. So you can see, and you guys can just try it out. There's nothing that says. So this is what I mean by shorts, right? Yeah, okay, it's going to come in a little bit. But it's running the simulation probabilistically, and you'll see.
So Roopesh, this is the result of running it a few hundred times or something?
Yeah. So you ran it 1,024 times. So you got 0, 0 in the 779 times, and then 245 times you got 1, 1. That's what it means.
So it's 75%
Yes.
roughly
Yeah,
accuracy right now.
Yeah. But this is a different thing, but still, yeah. This is probabilistic. Everything is probabilistic here.
Right.
So, guys, I've shared this all with you. We'll send the link and then you can try it out. Okay.
Thank you.
Thank you.
All right, thank you.
Thank you so very much, Roopesh. I'm going to speak for myself, maybe others. I think this was a fascinating talk. You know, I think first of all, you covered the gamut. So often you just get one deep sliver into deep. This was really great for us. Hopefully this has ignited curiosity. I, for one, know I'm going to go back and look up some of these things that you talked about. So it's great, and this is really, I want to thank you, Roopesh, for getting us all educated on this today. And hope next time we have you, we can get more in depth into something, and hope to see more of you all in these tech talks. And again, if there are any topics you want to either see IIT-AGNE host, or you have some ideas, please share it with us. And hope to continue to see you all out here. Thank you so much for coming today.
Sure.
Thank you.
I have some books here. If anyone wants to take a look at some of the books that are there. And I also have my card because this is actually, business development. Anybody wants to talk? BizDev. So I have my card here. Anybody wants the card?